Okay, in this video we'll go on to talk about 2005 AB1, which is also an area and volume free response question. So we have these two curves, f of x, which is the sine curve or some transformation on the sine curve, and g of x, which is an exponential curve. And R is the shaded region in the first quadrant that's enclosed by the y-axis and the graphs of f and g, and S is the shaded region in the first quadrant enclosed by the graphs of f and g as shown in the figure above. And so the first thing that we would need to do here is to actually go in and find the points of intersection here. So we'll bring up the graphing calculator, and I have the two functions here. F of x, which is the sine curve, is in y1, and g of x, which is the exponential curve, is in y2. So the first thing that we would need to do is to be able to find the points of intersection, which I've already labeled, but I'm going to go into graph, and sorry, I need to turn those two on, and go to graph them, and you can see the region that we're interested in there. So second, calc, intersect, first curve, second curve, and enter for guess, and we get the 0.178218, etc. for the x coordinate and 0.78109 for the y coordinate. And I've rounded them to 4 decimal places. But what I want to do is I want to store those into variables that I can later on, or user-defined variables that I can use later on. So the way that I'm going to do that is go back out to the home screen, and you can see that when I hit X, it gives me that 0.1782, and when I type Y, which is alpha and then 1, it gives me that Y value. To store them, what I'd do is X store alpha A. Now, because those are system variables, they can get written over, whereas only I have the ability to write over the user-defined variable A and B later on. So I've stored the x coordinate into A, and I'm going to store the y coordinate into alpha B. And now I can reference them later on. Now the next thing that we need to do is to find the other point of intersection. So second, calc, and intersect. And we found that left point of intersection already. And so first curve, second curve, and guess gives us 1 and 0.25. And so I'm going to label those C and D. These are not as bad. They're easy to remember, but I'm still going to store them. And I can just type in the number 1, store alpha C, and 0.25, store alpha D. So I have them all in those variables there. If I need them. I'm not likely to need the y coordinates, but I will definitely use the x coordinates. Alright, so what I want to do now is to set up my integral, and I'm going to close down the calculator for a second, and for part A, then my integral would be the integral, and the limits of integration are going to be from 0 to what I've called A, and the top function is g of x, so g of x minus f of x dx. Go back to my calculator, go back into y equals. This time I'll shut off both of those, and begin now. So I need g of x, which is y2, so variables, y variables, function y2 minus variables, y variables, function y1, and that should set it up. That's g of x minus f of x. Go back out to the home screen, and my integration is on math, option 9, and my function is in y3, so it's variables, y variables, function y3, comma, variable of integration is x, starting point is 0, and the ending of that interval is a. So I hit alpha a, and I don't need to type in that whole long number. And we end up with 0.065 rounded to 3 decimal places. Alright, then we're ready to go on to the second part, which is to find the area of the region S. And so here the two functions have changed. F of x is now above g of x, so I'll set up the integral. And so what I want now is the integral from a to c of f of x minus g of x. Go back into y equals, and I could change 3, but I'm just going to leave everything in case I need to come back to it at a later time, and I can clearly see what I've done if I make any mistakes. So vars, y vars, function y4 in this case. Oh, actually, y4 is where I'm putting it, so I want y1 minus y2. Clear that out. Vars, y vars, function y1 minus vars, y vars, function y2. And all I'm going to need to do is go back out to the home screen, call up the last command. This time I'm going to change my function to y4. Variables, y variables, function y4. And my limits of integration this time will go from a, alpha a, to alpha c. Or just type in 1 there. And I'm ready to go. And that gives me 0.4103. And we can tell that that's much larger than the area of region R. So 0.410 would be rounded to 3 decimal places. And that's going to do it for part B. Now we'll go on to look at part C. In part C, we want to find the volume of the solid generated when S, only S, is revolved about the horizontal line y equals -1. And so again for this, I'm going to set up, I took a little snapshot of the graph there, and we want to revolve the region S about the not the x-axis, but parallel to the x-axis, the line y equals -1. So we'll set something like that up. And again, not necessarily drawn to scale there, and we're going to revolve each curve around that line there. And this is going to give us washers, and the inside circle will be the curve g of x. And then we have a little thickness to it, and that's going to be dx. And so our area for the area between the two concentric circles is pi capital R squared minus pi little r squared. And capital R squared is going to be f of x, but it's f of x plus 1, or f of x minus -1. So, and little r will be g of x plus 1. In both cases, because we go from the curve to the x-axis and then 1 unit below that. So it would be whatever f of x is plus 1 for capital R, whatever g of x is plus 1 for little r. And we're ready to begin setting up our integral. So part C, we bring out the pi, and again this time we're going to go from A to C, and we need capital R squared, which would be f of x plus 1 squared minus g of x plus 1 squared dx. And all we'll need to do now then is to use the calculator to find those values. And I'll bring up the graphing calculator here. And we're going to go back into y equals. and I will turn off y4. We'll start a new one, which will be y5. We'll need the pi times f of x, which is y1 vars y-vars function y1 plus 1 quantity squared minus g of x, which is y2 quantity variables y variables function y2 plus 1 quantity squared, and then another parenthesis there, so that pi is distributed to everything. So it's pi f of x plus 1 quantity squared minus pi y g of x plus 1 quantity squared. We'll go back out to the home screen, call up the last command. Now we want to go y5 variables y variables function y5, and our limits of integration are still from a to c, and we get 4.559 rounded to 3 decimal places. And that's going to do it for part C and for this problem. So we'll close down the calculator there, and you can see the work that's needed for the 3 parts here. Again, all you have to do is set up your integrals correctly. You don't have to write all the numbers down. You can use f of x and g of x if they're clearly labeled on the problem sheet, and instead of using the many decimals in the limits of integration, we can save them and we can reference them as A and B or C, whatever it is, in the actual answers that we provide. So that'll do it for this problem.